Welcome to the Explainer. Today, we are going to do something pretty fascinating. We're decoding what we call the system beneath. Basically, we're going to investigate exactly how advanced technology is being used to detect hidden, completely invisible rip currents lurking right beneath the breaking waves.
Okay, let's just dive right in. Picture this. You're standing on the beach, or maybe you're checking out a surf cam online, trying to figure out where to swim. Human nature, and honestly just simple common sense, naturally draws our eyes to this dark, deceptive, calm spot. You see a gap where the waves just aren't breaking, and it looks like the absolute safest, easiest path into the water, right? Well, it turns out this visual intuition is a massive failure path in human perception. That tranquil, calm-looking gap, it's actually the single most dangerous place you could possibly enter the ocean.
To show just how deceptive this is, scientists will sometimes toss non-toxic green dye into the water, and when they do, the truth comes out instantly. That dark, quiet patch of water isn't resting at all. It's actually a highly concentrated, incredibly fast-moving offshore rip current, cutting directly through the surf zone. And we're not talking about a gentle pull here. The water in this narrow channel can move seaward at up to 8 feet per second. To put that in perspective, that is literally faster than an Olympic swimmer. The stakes here are incredibly high. In fact, these rip currents are responsible for about 80% of all beach rescues and roughly 100 deaths in the US every single year.
So how does this actually happen? We need to break down the strict causal sequence of how this hazard physically forms. You can kind of think of this like a layered engineering diagram. Step 1, you have uneven wave breaking, which is usually caused by a gap in a shallow sandbar underneath the water. Step 2, this uneven breaking creates variations in what scientists call wave setup, which creates high and low water levels. Step 3, because water naturally wants to level itself out, feeder currents start flowing along the shore. They're effectively flowing downhill from the high water areas to the low water areas. And finally, step 4, all that excess water converges at the low point and shoots straight offshore in a tight, narrow channel known as the rip neck.
Now, I really want to focus on that concept of wave setup for a second because it is absolutely crucial. When waves break, they push water toward the shore, and that results in a localized water pileup. This setup is literally the engine driving the entire rip current system. But here's the massive problem. This increase in the mean water level is usually only about 10% of the breaking wave height. It's this incredibly subtle, dynamic process that is practically impossible to see with the naked eye when you're just standing down on the sand.
And that brings us to a major crisis in observation. In situ human observation, which just means a beachgoer trying to make a safety decision at ground level, completely fails. When you're down on the sand, you suffer from a horrible vantage point. You can't see the depth, you definitely can't see the wave setup, and you easily fall victim to confirmation bias, seeing that calm water and assuming it's safe. The necessary handoff here is to an observing actor that doesn't share our physical limitations. We need fixed, elevated surf cams pointing seaward. These cameras provide this crucial objective, top-down perspective of the dynamic surf zone that we physically just cannot achieve ourselves.
If you're thinking to yourself, well, I know what to look for, I'd spot it, consider this rather shocking statistic from a natural hazard study. Researchers tested beachgoers on an actual beach. They weren't just looking at photos, they were evaluating the real, moving water right in front of them. Out of everyone tested, only 22% could successfully identify a rip current in person. Just 22%. Even people who easily spotted rips in photographs completely failed when they were actually standing on the sand. So the takeaway is clear. We simply cannot rely on human eyesight alone to spot this hazard. We absolutely need a system.
So here is where the digital handoff comes into play. We are moving from the physical movement of the water into a computational environment. We take a sequence of surf zone frames from an elevated camera and we pass it straight to software. The raw pixels showing breaking waves and calm gaps have to be translated into a rigorous mathematical system of observation.
And this brilliantly illustrates exactly how one side of that computation works. It's called the rip-viz system. What's super interesting is that it doesn't look for a specific shape of a rip current at all. Instead, it looks for anomalous behavior. First, it converts the video frames into an optical flow field, meaning it measures the unsteady 2D movement of every single pixel over time. Then it uses something called an LSTM autoencoder, which is a specialized type of neural network. The researchers trained this network on what normal ocean flow looks like, regular waves washing up and retreating. So when it processes a new video and sees water doing the exact opposite, flowing continuously out to sea, it immediately flags those anomalies.
The software actually creates short visual traces, called virtual path lines, to track this water movement frame by frame.
I love this because it's not some flashy sci-fi AI brain magically knowing where the danger is. It is a highly grounded causal tracking mechanism. Because the ocean is messy and chaotic, tracing one single long timeline gets way too cluttered. So the software traces short sequences of these path lines, analyzing the natural quasi-periodic flow of the water and essentially hunting for specific vectors that defy the incoming wave motion. To fully wrap our heads around this technology, we have to recognize that there are actually two distinct branches of computation being developed right now. The first method is the optical flow we just talked about, tracking motion anomalies frame by frame using LSTM autoencoders. But there's a second branch that relies purely on machine learning. This approach takes thousands of still images that human experts have already labeled and feeds them to complex models with names like Faster RCNN, YOLO 11, and Mask RCNN. Instead of tracking movement over time, these neural networks learn to recognize the visual patterns and textures of a rip current in a single image, eventually outputting a bounding box around the hazard.
But, and this is a massive but, the crucial point here is that this technology is definitely not perfect. It is a flawed instrument operating under strict system constraints, and we have to map out its failure paths. First up, flash rips. These are highly transient, sediment-filled plumes caused by short, choppy waves. They don't have stable visual signatures, making them incredibly hard for a vision model to lock onto. Second is environmental noise. Things like harsh sun glare on the water can completely corrupt the camera lens and totally trick the optical flow software. And third, camera limitations. If a camera isn't positioned low enough or pointing seaward enough, the mathematical geometry of the whole system just fails.
To put a hard number on exactly how uncertain this is, we have to talk about 67.3%. In a massive recent study that used optical flow to track over 20,000 rip currents across multiple beaches, the average accuracy for detecting a rip current was 67.3%. This number is so important for us to understand. It reinforces that we are dealing with bounded, uncertain detection. The software is an incredibly powerful tool for sure, but it is not an omniscient oracle. It absolutely misses things.
Because of that level of uncertainty, we must be crystal clear on where the data goes next. The digital handoff is ultimately followed by a human handoff. The output of these systems, whether that's anomaly points or bounding boxes on a screen, never ever makes an automated safe-to-swim decision. Instead, those observations are handed off to scientists, forecasters, and public safety partners. They use the data to validate hazard models, to understand spatial trends over time, and to improve long-term forecasting. It's a scientific instrument placed inside a broader human coordination network.
Which brings us to our ultimate takeaway from this explainer. The value of this technology is not omniscience, but rather making a dynamic, hard-to-see process inspectable enough for better human coordination. Think about it. We took an invisible physical engine, wave setup and feeder currents, and used fixed cameras and advanced algorithms to actually render it visible. It doesn't replace the lifeguard on the beach, and it certainly doesn't give you an automated green light to go swimming, but it does give us the hard data we need to coordinate, adapt, and stay safe. It really makes you wonder, though, what other invisible systems are operating right under our noses just waiting for the right lens to finally be revealed?